Hello students, welcome back. Now let's go to problem 1b. 1b is the 95% upper confidence bound. Now this is different from problem 1.1. It's not the upper bound of the 95% confidence interval. Previously we got this confidence interval, 95% confidence interval, and what do you mean by 95% upper confidence bound? Does it mean by the upper bound of the 95% confidence interval, 63.11? No, that's not it. Here's the initial picture associated to 95% confidence interval. Here, 95% is concentrated in the middle. That's what the confidence intervals are all about. Intervals start from here, x1, and end at x2. We need two bounds, lower bound and upper bound. And that's what confidence intervals are all about. Now, how about upper confidence bound? This is a little bit different. We're looking for an open-ended interval like this. Now, for this particular example, the upper confidence bound does not make too much sense, as a matter of fact. Yes, for the sake of exercise, we can force it in, but it doesn't make too much sense. But if this is some highly sensitive security system, let's consider something drastic like nuclear reactor. In that case, if the system is running exceptionally well, you don't care about that. It's the failure that you're interested, and then you want to control that part. So whether something is happening here, well, if it is exceptionally well, then exceptionally well, it just goes on, no problem there. It's only this part that you're interested in. So if you have upper confidence bound or lower confidence bound, the confidence interval actually goes to negative infinity like this, or positive infinity the other way around. And 95% is not just middle, but all the way to the left. And this part over here is 5%, not 2.5%. Previously, here 2.5%, now 5%. So the picture tells us everything. As for the solution, oh, that's not too bad. Z is end minus center over, now let me just rewrite, end minus center over SE and it is x minus center over standard error. And that's associated to this z-score, where we have 5% here, 95% there. So let's go back to this z-table. And when do we have 95% to the left? To the left, I want 95%. Let's go down, 95, here we go, 9495 and 9505. 9495 and 9505. We have a push here. And then somewhere in the middle, you're going to get the correct z-score. So I'll estimate it at 1.645. So that's 1.645. Okay. And then let's solve it. Flip this denominator to the other side. X minus 60.0 is approximately equal to 1.645 times, I have to flip this denominator to the other side. So we have 4.95 over square root of 76. Flip this to the other side. We have x is approximately equal to 62.0, the mean, and a plus 1.645, the z-score, 4.95, the standard deviation over square root of 76. And let's do this computation. You can punch all these into calculator, but I have Mathematica here with me, so let me just use that. And this is what I got, 63.934. So that is my upper confidence bound, 95% upper confidence bound. You can approximate it a little bit further as 62.9 or 62.93. Either way, it's going to be okay. I did not specify how many decimal digits to take. So there you go, and that's the conclusion. Here, I decided to take just one decimal digit, and that's actually appropriate here. Original problem was given in terms of one decimal digit. We have 4.95, 2 decimal digits, so you can argue that you're going to need 2 decimal digits if you want to, but either way it's going to be okay. In any case, it's going to be okay as a matter of fact. As long as you did something like this, it's going to be okay. So, upper or lower confidence bound problems are actually easier than confidence interval problems in a sense that you need only one bound. Associated pictures are a little bit different. So that's where you may lose some credit if you do. So upper confidence bound. So the upper part is what you want. So that's the shaded part. And then the other part is 95%. If you have multicolor, that's good. We have blue and red like this. But if you have just one color, just pencil, then usually it's a good idea to shade to the right because this is upper confidence bound, so crossing that part out for 5% is usually better. But if you shade here to the left and write down 95% somewhere here, that's going to be acceptable too. Okay, we are done with first 2 problems. Now let's go to number 3. If the 90% upper confidence bound is 63.5 miles per hour, what is the standard deviation? We don't know the standard deviation, so 4.95 no longer applies here. And 90% upper confidence bound is 63.5. So we have this kind of initial picture. See, to the right, I have 10%. See, I have 10% here, and that happens to be 63.5. So that's the initial picture. If you have 2 colors, you can shade blue, red like this, but if you have only 1 color, shade to the right, and that's 10%, 90% there. Okay, and that happens to be 63.5, and from this, can you find a standard deviation? Well, z-score is n minus center over SE. But then again, what is this? Let's take bigger font. N is 63.5, center is 62.0, and then the standard error is standard deviation, which we don't know, and let's see, S over square root of 76. And that's approximately equal to the z-score associated to 90% here, to the left, 10% there. So let's look up the table and let's find out the z-score associated to 90%. So this has to be 90%, so let's look for 90% somewhere here. 0.8997, this one is the closest. 1.28, do you see it? So this is going to be approximately equal to 1.28. And from here, we can find out this standard deviation, which I just highlighted in red. Okay, ready to go? Okay, all right. Let's go ahead and do that. Let's switch these two. Basically, I can divide both sides by 1.28 and put it down here, and multiply the denominator to both sides so that I can go over there. So the conclusion here is s over square root of 76 is approximately equal to 63.5 minus 62.0. Oh, excuse me. Okay, let's do this over. 63.5 minus 62.0 divided by 1.28. What did I just do? I switched these two. And this is the quantity you're looking for, the standard deviation. One more thing to do, flip over this square root of 76 to the other side. So s is approximately equal to, and this quantity, I didn't calculate them yet, but you're welcome to calculate whenever you're ready. And square root of 76. We just multiply this denominator to the other side. And then let's calculate all these. I have Mathematica with me, so calculation is simple for me, just copying and pasting. For most of the students, it's going to be a bit cumbersome because you have to punch in all these in the calculator. In any case, this is what you have. The standard deviation is about 10.22, I'd rather say. By the way, I use S, but if you want Greek letter sigma, go ahead and do that. Go ahead and do that if you want to. Or if you're not really familiar with anything, just write SD there. Standard deviation over square root of 76, and standard deviation is this quantity. In any case, whatever symbol you use, it's just an algebra problem. Solving an equation. It's just a linear equation. Let's see, do we have a solution here? Yes, exactly the same thing. Changing this and that, so we get this equation, and flipping this denominator to the other side, we get that. Okay, what did we get? We got sigma. The standard deviation is about 10.22. Okay, we're going to use this to answer the final problem here. 97% confidence interval using the standard deviation from here. And let's see. 97% in the middle, so 1.5% there, 1.5% there. And we are going to be using 10.22 as the standard deviation. How do you do that? Well, I'd like to save time. This is just a repetition from previous problem, except we have different standard deviation value. So I can afford going quickly here. And then end minus center over SE is equals to negative 2.17. If you look up this Z table, associated is to 1.5% or 0.15. So we get this equation. Flip this denominator to the other side, like this, and then flip this center, this subtraction to the other side. That's what we get. We have 1. And then change the minus sign to plus. We have the other, and that's the conclusion. We're using the symmetry as before. And we got this value and that value. Picture is important. You can visualize why we're having minus and plus from the picture. Okay, that concludes problem 1.